So, class, welcome to module 1 times 10 to the 5 divided by the derivative of the sine function around its midpoint evaluated there very nicely, since sine is a nice smooth function. So, now I'm glad you at least know the module number, which is a brilliant place to start learning the module. Let's talk about the meat of it. So this is quantum mechanics, and joining us this semester is a student all the way from the lands of the Lion King. So please meet Simba. Simba is an avid learner of quantum mechanics. He really is excited to be here, aren't you, Simba? Yes. I've always wanted to learn quantum mechanics. I love particles. I love so much. I've seen Simba clearly. I'm so excited. This is exactly why I came to uni. Oh, this is going to be so much fun. And I'm so glad that Simba is so excited. We're going to learn so much quantum mechanics together. Anyway, brilliant to have you here, Simba, and I'm sure by the end of it you'll learn all the quantum mechanics you've ever learnt and, won't have any questions left. Oh, thank you, Professor. Thank you. So let's now begin looking at our lovely old friend, well, something that will be your friend and also a living nightmare, the wave function. So, firstly, Simba, what do you think a particle is? I think a particle is a ball. Well, no, Simba, you are completely and utterly wrong. You need to throw away all you have learnt in GCSE and A-level because it is completely sensible and therefore completely incorrect. A particle, as I hope most of you realise, having spent your life with them and having been made up by them, a particle is something as simple as a irreducible representation of a Poincare group. And due to your studies in special relativity, which I'm sure you all remember, since your first year summer break, I'm sure you'll understand completely what a Poincare group and will need no further reminders. So, now we are all clear on what is a particle, are we not, Simba? I don't think I really would. What is a Poincare? Brilliant. I'm glad we fully understand a Poincare group so swiftly moving on. What is the professor doing? I don't know. How am I going to complete my homework? How I need to switch to another major. What's going on? So now we have a clear understanding of what a particle is. We can progress on to the next topic of this quantum mechanics course, because I know you all, do not want to be spending too long, so I'm making sure that we move at a very good pace, although it is perhaps more leisurely than some of you might like. So, now we know what a particle is. How do particles behave? Well, particles behave according to this equation, and our Greek symbol, who you will have, regular nightmares about, called psi, the trident-like symbol, is the wave function, but I'm sure just looking at the equation you're already getting a very good physical intuition for quantum mechanics, aren't you, Simba? Yes, well, I'm not sure, but I'm sure it'd be all right. But why is there an I? Why is there a square root? Exactly. Well pointed out, there is a square root of a negative number, so clearly all of Newton's laws do not apply here, because they do not describe matters with imaginary numbers, making Newton's laws imaginary and quantum mechanics real. And now, what though can we do with it? Well, this beautiful Schrodinger's equation doesn't tell us about how particles interact. It tells us about what they're doing when they don't interact. But using the fact that this equation is a linear differential equation and the fact that due to linear algebra we can play around with this, we'll look at interactions in a little bit, but I'm sure you can already get a sense of where I might be going with that. But how do we get, even when particles are not interacting, standard things like energy levels out of this equation? Well, you're familiar with the separation of variables, so we just apply that here and use Fourier analysis, which you have all been given a very large textbook on during your first year, which I'm sure you have all read and can practically memorise all the details of. So it's a simple exercise which I leave to you to show you that we end up with this equation for the time-independent wave function, from which you can deduce the energy levels E, which are your eigenvalues of your first-order differential equation. Does anyone have any questions? I have so many questions, but I'm so confused. I don't even know which equation to ask. I mean, what is that? What is that upside down triangle? Why are there triangles? What's happened? Where has the square root of -1 gone? I don't understand. I prefer Newton's laws. Can we just go back to classical mechanics? And so now you fully understand all of this, or can you spend hours at home doing my job for me, because I'm technically getting paid for this, however my passion is in research, and I have no actual interest in teaching. But anyway, if you want to become a researcher like me, you will need to understand this equation. And am I going to show you how we get energy levels for it? No. There's no real point me doing that. I mean, you're here to study quantum mechanics, so you're clearly motivated people. So I'll leave it to you to show that quantum mechanics has quantum embedded into the heart of it, and quantization. Good luck. So we have seen how particles, what they do when they're not interacting. We discussed, or really summarised, what a particle is. And so now we're ready to move on to the meat of quantum physics, which is how particles interact. Because it's interactions that cause things like particles decays, cause, particles to bond together to form composite particles, like how quarks can bond together to form nucleons. So this is a very, very important topic. And I would say if you don't get this topic, then you don't get anything in physics. Because without this topic, well, life wouldn't be possible. We would just have, uninteracting fundamental particles, so we wouldn't even have an atom. So all of physics really rests on this, and so it's vital, absolutely vital, that you understand the material I'm going to cover, which is why I'm dedicating an entire slide to it. So very important stuff here. So, if you want to look at how particles interact, you take the differential equation I've shown before involving the complex function of the wave function, and then you treat that complex function as a complex vector living in a Hilbert space. And then with this Hilbert space, you can think of the differential operator as an infinite matrix. And then, using matrix expansions about the eigenvalue problem, you can find the results of interactions on the wave functions and, more importantly, the energy eigenstates. So all you do is you simply turn the first thing into the latter thing, so you go from psi to psi dot arrow 0, and I'm sure all of that makes complete and utter sense, because you've seen vectors and functions before. You've been using them since GCSE maths, so I'm sure you're perfectly familiar with what to do. And Rule 101 in physics is, in the past I've had some students ask me, what is the physical meaning of this perturbation about an eigenvalue problem? Well, to that I can only say we are in a physics department. If you want to insist that the maths has some physical meaning, or to get a picture of what's going on, then please go to the philosophy department. They have the resources available to help you, whereas here in the physics department, we really do not have time to ask questions about what on earth is actually going on. But anyway, I hope all of this maths is fairly straightforward, and you've seen vectors and functions before, so you'll be fine. It should be fairly okay. So again, Simba, any questions you have? I do have one question. The zero, is it like to the power zero? Are these powers? Are these tensor indices? There's a lot of new notation here. Brilliantly spotted, Simba. That there is new notation here, and here in physics we put numbers everywhere. We put them before letters, after letters, sometimes even inside letters or inside operators, as those of you who have done path integrals before will probably be familiar with when looking at things like fluxes. So, yes, well spotted, exactly. There is a number, and I leave it as an exercise to the reader to explore all possible things this number could mean and then pick the most likely one. And if you're good at probability, you then got a high chance of knowing the material, so you have a hope of passing the final exam. That's the exam? But I barely understand anything that's going on. But I must spend hours in the library. I don't, what am I going to do? Oh dear, oh no. Oh dear. Oh, why did I do physics? So, as I'm, fairly happy with how much we've covered, and I think, I've been really concise. Um, we're already ready. After just a few minutes, having summarised the entirety of what you need to know for quantum mechanics, albeit providing you do a few hundred proofs, which I leave as an exercise to you to really kind of investigate what I've been saying. I'm ready now to introduce the marvellous bits of physics that we're going to be doing next semester, building on from this fairly straightforward material, because I'm sure you want something a bit more challenging that you can really sink your teeth into. A bit more, no, too fast. We need 4 semesters. What's happening? Soon they're going to tell us that all of quantum mechanics is wrong, and we have to replace this bizarre wave function with something else. And I don't know what's happening. Why can't we go back to Newton's laws? I like acceleration. Please, stop with the quantum stuff. Well, as I'm sure you'll be glad to know, next semester, given that this semester has been filled with really boring quantum mechanics, next semester we'll be looking at quantum field theory. And in quantum field theory, you'll learn lots of cool things, including that everything I've taught you here is wrong, and actually wave functions don't even exist. Okay, don't crack glass. Simba has unfortunately had a moment where he's fainted, probably due to excitement about looking at quantum field theory. So, the chat might be a bit down because, you might not have somebody to help with the homework, but don't worry. If you have any difficulties, come to me and I will give you a booklet of integrals. Anyway, now I've reassured you, A note about the oncoming exam. In the oncoming exam, all numbers will be written in binary in the exam paper, and for you to get any marks, you will also need to give your answers in binary. Um, and so I might advise that over the Christmas holidays you brush up a bit on computer programming just to ensure you're ready to write very long decimals and perhaps even approximations of irrational numbers in terms of binary. And a small aside, you might wonder what's the point of this? Well, it's highly likely you'll never actually use any of this information in your daily life, but I'm certain that you will spend the rest of your life worrying about how to physically interpret it and spending hours kind of like feeling like you're bashing against a wall, attempting to understand what the wave function actually is. So, I have given you food that will haunt you for the rest of your life. And with that, I think we have finished this semester. It has been a pleasure summarising quantum mechanics, and I cannot wait to get back to doing research.